Alright, there's two kinds of alkynes that I want you to be familiar with. You can either have something called a terminal alkyne, which has a hydrogen on the end of it, or you could have something called an internal alkyne, which doesn't have a hydrogen on it. So it should be pretty straightforward. Notice this alkyne here is in the middle of this molecule, so it's an internal alkyne. So terminal means end, like think of a terminal of a bus line. Okay, so you're going to the end of the bus line. So here's an example of a terminal alkyne. So go ahead and label these: internal alkyne, terminal alkyne. Now notice the terminal alkynes are the ones that have the hydrogen on their sp2 carbons. Okay, so all of these alkynes we were talking about before, right here with pKa 25, that pKa is referring to this hydrogen. If I had an internal alkyne, I wouldn't have a hydrogen on that carbon. So then the pKa is up here, right? Because you don't have the hydrogen on the sp hybridized carbon. It has to be on this carbon for it to have that pKa value. So since we have a terminal alkyne, it's terminal on both sides actually, so it turns out we can use a strong base to deprotonate that. So we use a base like hydroxide. It's our classic example of a strong base. Grab the hydrogen and break this bond and give it to the carbon as a lone pair. So we need to practice our electron pushing, remember? Alright guys, so this is what I get. I get the base reacts with the H plus here. This breaks off, gives a lone pair to this carbon, and here's that more stable conjugate base again, right? That we saw before. So let's practice that again. Base always grabs the H plus of an acid. Let's do that here as well. Base grabs the H plus of an acid and this breaks off like that. Okay, draw me what you get from that. Now the sodium is, I could have had a sodium up here as well. We usually have sodium hydroxide. So that means it's just a counter ion. It's floating around spectator ion, right? So you can just put it here if you want. But usually I just ignore it because it's going to cancel on both sides, and usually we deal with net ionic equations. But you know, if they show it, go ahead and put it down because it balances the equation. So now let's take a moment and answer some of these questions to help us understand what's going on. Based on the approximate pKa of a carboxylic acid, so here's my carboxylic acid, pKa is about 5. Label the stronger acid versus the weaker acid on each side of the equation. So here's my acid on one side and my acid on the other side is here. Do you guys remember the pKa value for alkynes in general? It's about 25. So who's my stronger acid? It's going to be my carboxylic acid. So that means strong pushes to weak. This is more reactive, so the reaction is going to push in this direction. And I drew in my arrow going to the left up here. So what this is telling me is that if I want this hydrogen to come off, I'm going to have to use a stronger base than this. The reason why this base isn't very strong is that its conjugate acid not as weak as it could be. Okay, so pK5 is still a weak acid, but it's on the bottom of the chart. It's still pretty stronger than a lot of other things we could have chosen. So let's think about why this is not as strong as hydroxide. Do you guys remember structurally how you could tell that this negative charge is not going to be as strong or as dense as this negative charge up here? Well, I hope you guys are thinking of the R word, R, resonance. Okay, resonance stabilization means that these electrons are more spread out and not as forceful on this hydrogen to deprotonate it as it is up here. And if you look at the pKa of hydroxide's conjugate acid, which is water, this is a pKa of about 16, right? 15.7. So when you can make this much weaker, then the reaction will get pushed forward. Okay, so let's do a couple more and then answer this question. Why don't you guys go ahead and pause it and give this a try. Alright guys, so looking at this reaction, I've done my electron pushing and I'm showing my conjugates. I'm looking at the pKa of these resulting acids. And now I want to know, what does that pKa have to be for this reaction to be strongly product favored? So basically, remember up here, when my pKa was low, that means this acid was strong, so it pushes to the left. So what I want is for this to be a high pKa. So this is not too shabby. The pKa of the alkyne was 25. 16 is getting close to 25, right? But it would be even better if it was greater. So if I want my reaction to get pushed forward, I want this to be a weak acid. So it's going to have a high pKa. The higher the better. Now this 16 is not quite as high as 25, but it's getting there. And so if it was even greater than 25, that would be great. So I'd want the alkyne to be less than the pKa of the conjugate acid of this base. Okay, so I want this to be as high as possible, making this weak and making the reaction push forward. So here I would say it's sort of going to be equal. It's probably going to be a little bit more this way, go a little bit more reactant favored than product favored. Here this is definitely much stronger than 25, so it's going to be even more product reactant favored here. So this is definitely reactant favored, and this is also reactant favored, but this is going to be a little more spontaneous than this one because it's not as reactant favored. I hope that makes sense. Another thing that I've taught students before is just to get a ballpark answer for the KEQ of the reaction. So the KEQ is sort of the difference between the pKa's of what you're starting with versus what you're ending with. So if I have a pKa of 10 here and a pKa of 25 here, clearly this is stronger as an acid than this is, so I'm going to be pushing to the left, and it's approximately 10 to the difference in pKa units. I'm going to add a negative here because it's going to be less than 1 because I know it's going in this direction already. And then the difference is 15. So not very product favored at all. Not very spontaneous, right? So ammonia and alkynes don't really react very much. Now when we look at this one, tert-butoxide, we know that's a stronger base than ammonia because of the negative charge. So let's see what happens here. So for this one, I know that the reaction is going to have a smaller difference. And this is a weaker acid than this is, so this tert-butanol is going to push a little bit to the left, but not as much as my first reaction here. So I've got a difference of about 9. So now you can see how much better this second reaction is. But a reaction that would be even more product favored, so these are reactant favored. If I wanted a product favored, what pKa would I want for this acid here? I'd want it to be greater than 25. I'd want this to be the stronger acid pushing the reaction to the right. So in general, you want this to be a very weak acid that gets formed. So if you could make something with a pKa of 35, let's see what 25, what's above 25? It's actually something like ammonia, right? So keep that in mind for later then. What would the base be to make ammonia? And that's really what will be an excellent reaction, very product favored.